All right, so the first question number 1 says that physical quantities are either scalar or vector. Select the row of the table which correctly identifies a scalar quantity as well as a vector quantity. So scalar quantities are one with. Hello? Hello, Farwa, can you hear me?
Yeah, I can.
Yes, so scalar is a quantity that lacks direction and vector has direction. So power is a scalar, velocity is a vector, so cannot be the answer. Weight is a vector, work done is a scalar. All right, over here we need a vector quantity. Work done is a scalar, cannot be the answer, so option D. Question 2. The unit of viscosity of fluid may be expressed as Pascal second. Which of the following expresses Pascal seconds in SI base units? All we need to do is just convert the pascals because second already is a base unit. Pascals means pressure.
Force over area.
And pressure means force over area. Okay.
That's
Force,
kg.
force is kg ms minus 2 divided by area is m squared. So this becomes kg m minus 1 s minus 2, right? The unit for pascals becomes kg m minus 1 s minus 2, and when you multiply this by the second, it becomes kg m minus 1 s minus 1. So that's the answer of question 3. A material undergoes significant plastic deformation under compression. Which of the following describes this material? Plastic deformation, and that has to be significant, means it significantly changes its shape. So it changes its shape. Okay, this might not be a part of the syllabus, but it most probably has to be C, because malleable actually means changes shape without breaking. So malleable is a, and it also undergoes significant deformation.
Also, what's the difference between ductile and malleable?
Ductile means that it could be drawn into thin wires, and malleable means it can change shape without breaking.
Okay.
Yeah, these are properties of metals. 4 says the manufacturer of a car claims that car can accelerate from rest to 30 meters per second in 7.5 seconds. What is the average acceleration of the car over this period of time? So can you calculate it?
Yeah.
What's the formula?
V minus U over T4. The answer is 4.
Answer is 4, option C. All right. Yes, correct. Moving on. 3 spheres P, Q, and R of the same mass are lifted from ground and suspended from a rigid support as shown over here. P, Q, R. This is your rigid support. This is your ground. Now the greatest change in gravitational potential energy is seen in sphere. Okay, these are lifted from ground and moved over here. C. Why C? Because when you apply the formula mgh, C has the greatest mass as well. But what about the height? The height is not the greatest, but the mass is greatest. If you look at the height of P, it's also large. So let's look at the answer options. I think Q alone, R alone. Okay, there is one option which is R alone, or okay.
Wait, I don't get it.
Sorry?
I don't get it.
What did you not get?
Like, why is it not P and Q?
Oh yeah, it is P and Q. Okay, why do you think it's P and Q?
Because it has more height.
Yes, and the masses are constant. If you apply the same formula mgh, mg is constant, and so the gravitational potential energy mainly depends upon height. So yeah, it's P and Q. That's the answer, because both of them are at the same height. Option B.
Can you check the marks?
Yep, that's the answer. 5 is B.
Okay.
Yep. All right, I'll check it again. Here you are, is B. And A is not correct because Q has the same gravitational potential energy. C is not correct because R is lifted through a smaller distance.
We can move on to the next question.
All right then. Graph shows extension of a spring varies with applied force. It's not a straight line, so it's not following Hooke's law, right? So now they're asking us which expression best describes the work done and extended the spring. Okay, so but look at the axes. Are the axes the normal conventional?
The top part is the work done.
Yeah, correct. So you are getting it. This is the work done. So if this is the work done, then how can you calculate the work done? Which expression? Let's see which expression would give us the work done. Okay.
C.
Option C or D. Okay. It cannot be half.
Wait. B.
B. Are you sure? B is the case when you have a straight line passing through the origin, and then this is your x-axis and that's your y-axis, and meaning that's the f and this is the x, and in this case the area, if you want to calculate, it's going to be half fx, half f1 x1.
Right.
It's not a straight line, and
so it's C.
it's
D. D.
It's more. Yeah, it's option D.
D.
Yep, that's the answer. That should be the answer. Let me check. 6, right? Yeah, that's the answer. Option D.
Okay.
Yeah. So now displacement time graph for the motion of an object is shown over here. Which of the following statements is correct? Okay, if you look at the displacement, as time passes, displacement increases, but a time comes when it starts flattening out. In displacement time graphs, it's the gradient that shows the velocity of an object. So now let's look at the options. There is a decreasing resultant force acting on the object as a direction in the direction of the motion. Well, we can't say anything about that. Let's look at option B. There's an increasing resultant force acting on the object in the direction of motion. There is a resultant force acting on the object in the opposite direction. There is no resultant force acting on the object. If you look at the gradient of this graph, it was maximum initially, but as time passes, the gradient is decreasing, right? If the gradient is decreasing, we can say that the velocity is actually decreasing, and the velocity decreases when there is a negative acceleration, and acceleration is negative when the resultant force on the body is in the opposite direction to the direction of the motion of that body. So which option had this? There is a resultant force acting on an object opposite to the direction of motion. It's option C. Get it? Box is placed on a table. The box and table are both stationary. This is table, this is box, this is floor. The diagram shows the direction of forces acting on the box and on the table. Okay, so Newton's third law, if you remember, force applied by the box on the table and force applied by the table on the box. So let's see. First says weight of the box and then the force of the table on the box, and the second says force of the box on the table and weight of the table, okay, and this says a floor force of the floor on the table and T. So which pair of forces are equal in magnitude according to Newton's first law? Okay, we need to just check out the forces which are equal in magnitude. So what do you think, which should be the answer? Which force should be equal to the other one? Normal reaction force always balances out the weight, is it? So the weight and the normal reaction force have to be equal to one another, right?
Yeah.
So that should be our answer, weight and normal reaction force. Whereas the weight of the table, this force which is due to the table, and then the weight of the box itself, when you'll add them, then the force of the box on the table, that's actually the weight of the box itself. This is the weight of the box, and they didn't give us WB equals to FT anywhere. So we don't need to worry about that as well. The force of the floor on the table and T, floor, this NT, this one, that the floor exerts this force, this will also be equal to the sum of the other two. The NT is gonna equal FT plus WT, but this option is not given anywhere over here. So We don't need to look at it. Does this make sense? Upward forces
Yeah.
balance out the downward forces. Which pair of forces are equal in magnitude according to Newton's third law? Newton's third law, for Newton's third law, just look at the on and by pairs, or the by or on pairs. Okay, so Ft and Nb, let's look at them. Where is it? Force of the box on the table, Ft. Force of the floor on the table, no, they are different. The box is applying on the table and then the floor is applying on the table. So they are not Newton's third law pairs. The objects should be the same. Objects shouldn't differ. Okay, over here we have the box and the table, and over here we have the floor and the table. They should also have been box and table. So that's not the answer. Option B says NT and NB. NB is force of the table on the box and force of the floor on the table. Again, the force, the objects are different. Again, that's not the answer. WB and NB. WB and NB. Now, these are the two forces on the same object, not by two different objects. So, again, and WT and NT, let's look at them. Weight of the table. Weight of the table, and NT says force of the floor on the table. Weight of the table is actually the force applied by the table on the floor, and this is the force applied by the floor on the table. So this seems like the most appropriate answer. WT and NT. Let's check it out. Number 9, FT and NB is the answer. Where is FT? Force of the box on the table and force of the table on the box. Oh, wait. Look at this option. Look at these two forces. This is force of the table on the box. We can call it force on the box by the table, and we can call this force by the box on the table. By the box on the table. It's these two forces which are the Newton's third law pairs. See, look at the wordings. Force that the table exerts on the box and force that the box exerts on the table. These two forces are Newton's third law pairs. FT and NB, it's option A, not D, it's option A. Clear?
Yeah.
Okay. Well, these questions can become quite tricky, so just do not forget this trick, on and by. On and by, and the objects have to be the same. They can't be different.
What's the on and by rule?
Meaning the force on the first object by the second object, and the force by the second object on the first object. Oh, sorry, by the first object on the second object, and by the second object on the first object. Look at these. The force which is applied on the box by the table. Box is your first object, table is your second object. And then the force applied by the first object on the second object as well. So see, I've just replaced these positions of on and by. Can you see I've switched their positions? That's how you identify the two Newton third law pair forces.
Yeah.
Okay, moving on to the next. Student investigated Hooke's law using the equipment shown. As each additional load was added, the new position of a marker along a meter rule was recorded and the extension calculated. Okay, loads are being added and then the extension is calculated. Investigation was repeated with an additional identical spring. Identical is the key term, arranged as shown over here. Now see, the springs are in parallel, and when they are in parallel, what happens to the spring constant? If this was a spring constant, what happens in this case? Since they are identical, it will divide by 2. Okay, remember the total spring constant becomes half when you have two springs parallel to one another, and when you have two springs in series with one another, their spring constants will get added. Oh, sorry, I reversed the statement. This is gonna get added. When they are in parallel, they'll get added. And when they are in series, they'll half, okay? Because in parallel, we apply the series resistor formula, K1 plus K2. And in series, we apply the parallel resistor formula. Remember, 1 upon KT equals 1 upon K1 plus 1 upon K2. That formula is applied over here to get the value for KT, which turns out to be K upon 2. So in this case, it's going to be twice of K. So we can say that these springs have now become stiffer than the first one. For a given load, applied load, which of the following statements is correct? Extension is doubled because the spring constant is doubled. Okay, for a given applied load means for a given amount of force. What happens? Which of these following statements are correct? Meaning for a constant force, which of these is correct? So we know from from Hooke's law that F is equal to Kx. Now, if F is constant, what's the relationship in between these two? K is equals to F upon X. F is constant, so K is inversely related to extension. Now, if I have doubled the K, the extension will become half of its original value.
Yeah.
Okay. And if it becomes half, so let's look at it. The extension is half because the spring constant has doubled. That's the perfect statement that we needed. Okay, option C. Moving on. A small stone is released at the surface of a lake. Immediately after it is released, the resultant force, downward force on the stone is this much. The stone initially accelerates through the water and then reaches a steady downward speed v. Okay, the resultant force on this stone is given to you, meaning the net force is given to you. So it is accelerating, okay? It has some acceleration and it reaches speed v, and it is released from the surface, means it had an initial velocity of 0. It is released. Diameter is given, viscosity of water is given. We need to calculate the value for velocity. This v is actually, what is v? That's the terminal velocity with which this stone is falling, because immediately after it was released, at that time this was the force that it had, but then as time passes, this force was the downward net force was balanced out, or it was counterbalanced by the upward forces. So therefore it moved with a constant velocity. So the formula that we could apply is that F is equals to 6 pi times eta RV. Out of this, the eta is given to us. The radius can be calculated from here. The V needs to be calculated. What's the force? Look at the question again. Immediately after it released, the resultant downward force on the stone is this much. The stone initially accelerates through the water and reaches a steady downward speed V as shown over here. When this stone had this much force downwards, right? This much force was applied on the stone downwards. In order to counterbalance this force, we have to apply the same amount of force upwards. And that same amount of force is going to also be 1 raised to the power of minus 5 Newton. This upward force is actually your viscous drag force. Viscous drag. So the value for F is the viscous drag itself. So you just apply that. So 1 raised to the power of minus 5 is equal to 6 pi multiplied by the value for n, which is 9 raised to the power of minus 4. And now calculate the value for V. Okay. For the velocity, it's 1. You just send everything else on the other side, so it's going to be 1 raised to the power of minus 5 multiplied by the 2 divided by 6 pi 9 raised to the power of minus 4 raised to the power of 1.1 raised to the power of minus 3 and
1.07.
Yep, that's the answer. Meters per second, correct. Now state one assumption made when calculating the answer to part A. Okay, so we'll need to assume something, right? This formula that we apply, this is for an oil droplet. Remember, in case of an oil droplet, we apply this formula for small spheres. Over here, we have assumed that the stone itself is also a perfect smooth sphere, okay? Assuming that it is a smooth sphere. You have to write the whole thing, okay? I'm just writing this. Another assumption that we could make is that the flow of the liquid is laminar, because laminar flow and non-turbulent flow would have a constant density. Remember
Right.
laminar,
Yeah.
non-turbulent. So that completes this question. Question 12. Okay, a boat held. Okay, this is vectors and scalars. So a boat held across a river towards heads to across a river towards x at a speed of 1.1 meters per second. As shown, the speed of the river from west to east is shown over here. This is the speed of the river. This is how the boat moves. Then they say the boat reaches the south river bank at y. The boat, it started steering in this direction, but due to the flow of the river, it didn't reach at x, but rather it reached over here at y. Okay, so now they are asking us to calculate this distance xy. What's this distance? Given that the width of this river is 75 meters. Okay, this is a pretty simple question, although it seems like a very complicated one. Basically, if you look at the arrows, these are the two velocities given to you, correct? If these are the two velocities given to you, you can use them. Okay, you can use the velocities to make a triangle and get this angle, theta. Okay, how am I gonna do that? Well, it's pretty simple. You pick up this velocity, 1.1, and place it over here in the direction given to you, right? From north to east, sorry, north to south. And then this velocity, you place it at the head of this vector, 0.55. Now you have a triangle, right? But this triangle cannot be used to calculate the length of xy. So what to do?
We can use the SOHCAHTOA rule.
Yeah, use the SOHCAHTOA rule to get the angle first. And once we have the angle and we have this width, then we can have this side as well. Okay, because we can use.
Or we can use the Pythagoras theorem.
Over here, no, we cannot.
No. Just find the opposite side, right? The diagonal.
This,
Yeah.
actually, this will give you also a velocity. This will give you a velocity because we've actually added two velocities together. This won't give you the distance xy, this one. Examiner wants this distance. So listen, what you need to do is first find this angle. How can we find this angle? Use tan of theta, right? Tan means opposite over adjacent. Opposite is 0.55, adjacent is 1.1. What's the answer? What's the theta? It's gonna be tan inverse of 0.55 upon 1.1. Can you calculate this out?
26.6.
26.6 degrees. Okay, now once you have this angle, you can calculate the value for xy. Now listen, this was a triangle of velocities, right? Similarly, you can make a triangle of displacements. Now see, this width given to you is 75. So this is a displacement of 75 meters. And xy is needed. So this is xy. This needs to be calculated, but the angle is gonna be the same as that of velocities, right? This angle is not gonna change. The angle given to you is 26.6. Now, once you have the angle and you have a triangle of displacements. Now remember, you cannot have a mixture of triangles of these two. You cannot have velocity and displacement in the same triangle. In the same triangle, you have to have the same quantities. So now this is a triangle of displacements. Use this angle to get the value of xy. Again, use tan of this angle. So tan of 26.6 will give you what? What is it equal to? Is it equal to 75 upon xy or the other way around?
Oh, the opposite.
Yeah, it's xy upon 75. Now get the value for xy. 75 multiplied by tan of 26.6 degrees. So what's the answer?
37.6.
37.6 meters. And I'm assuming that's the correct answer. Let's verify this one out as well. Yep, that's the answer. Accept anything in this range. Okay. Why isn't your answer perfect? Wait, it is perfect actually. They rounded off to 38, but that's the answer. You get the idea behind it?
Yeah.
13. Okay, a ball bearing is here, moves across a horizontal bench towards a magnet. Ball bearing moves towards a magnet. Now the velocity time graph for the horizontal motion of the ball bearing up to a point of the contact of the magnet is shown over here. Okay, this is a magnet, this is a ball bearing, and the ball bearing starts moving towards it. So look at the graph. This is your velocity time graph, and it's not a straight line. And if it is not a straight line, then that actually means it is a curve. Curve means that the acceleration is changing, it's varying, right?
Yeah.
So now explain the shape of the graph. Okay, you just need to first explain the shape of the graph. So first of all, the acceleration is negative, okay? And then as the ball moves, the acceleration becomes completely zero at a certain time period. And after that, the acceleration, it increases in the opposite direction and then reaches its maximum value until it hits it. So horizontal motion of the ball bearing up to a point of the contact of the magnet is shown. Okay, so what's really happening over here is that this is a ball bearing. First it starts moving, it is moving with a certain velocity. Let me draw it over here. It is moving across a horizontal bench, right? And if this is a bench, then it's not necessary that the bench is gonna be smooth. It can be rough. It can have
Because
frictional
of friction.
forces.
Because of
Yeah,
friction, the velocity decreases as well.
yeah. And after that frictional, that rough surface, it changes, or after the rough surface is over and frictional forces become zero, after this particular point, then the ball bearing velocity
Velocity
starts
increases.
increasing and the acceleration becomes positive. So the points you need to be careful about are these values of the time, which is 0.3 seconds, and the corresponding value of the velocity as well. It's better to mention that as well. The corresponding value of velocity at this time is approximately 0.9 meters per second. So till 0.9 meters per second. So the velocity, wait, it's not 0.9, it's 0.09. So velocity decreases from 0.29 to 0.09 with a decreasing acceleration as well. So initially it had negative acceleration up to 0.3 seconds. So up to 0.3 seconds, the ball had negative acceleration, meaning deceleration, as shown by the negative gradient of the curve. Then at 0.3 seconds, the acceleration became zero. And after that, the acceleration becomes positive because the frictional forces might have become zero after it. And the only force, or the net resultant force applied on the ball bearing, would be the force due to the magnet. Force due to the magnet after this particular time period of 0.3 seconds. Now let's look at the marking scheme. There's a deceleration and acceleration. Initial deceleration changes due to friction. The final is due to the magnetic force. Okay, we got all the points actually. Even so we did mention friction, then we did mention the forces of magnet, and we did mention both acceleration and deceleration. So yeah, this was a good question. Explaining the shape of the curve. Explain and describe are two different things, okay? Explain means you need to show, you need to write down why are they changing. And describe means you only need to just describe the pattern of the graph, okay? So both acceleration and deceleration exist. Okay, up to, you can mention the time as well, up to time of 0.3 seconds. Experiences deceleration due to frictional forces or drag forces of the bench. After the 0.3 seconds, the surface might have become smooth, so frictional forces might have become zero, and so the only force exerted is due to the magnet itself, and therefore has positive acceleration. Calculate the maximum acceleration of the ball bearing. Maximum acceleration. So you just need to see the point where the acceleration is maximum and it's positive. Okay. So for this, you just look at the graph and you'll need to draw out a tangent as well. So let me change this. Okay. So this point seems to be the maximum point. So draw out a big line. Okay, I don't have much space down there, but okay, let me zoom out a bit. Yeah, so
Okay.
wait just a second. You need to find out the gradient of this line. So and also for finding out the gradient, you must make sure that the 2 points that you select, they must be as far apart from each other as possible. Okay, so let's assume one of the 2 points is somewhere over here, this one. The other point should be somewhere down here, this one. Okay, so it's 0.5 and 0.0204. The other one is 0.62 and 0.42. Now use them, calculate the gradient, calculate the max acceleration. So 0.42 minus 0.04 divided by 0.62 minus 0.5. What's the answer?
Three.
Exact 3?
Yeah.
Okay.
Oh wait,
So,
no, wait. I missed the digit. 3.2. It's actually 3.16, so 3.2.
okay, 3.2. Let's verify it. Oh, 3.1. How close is that? And you check it. It's okay. So 2.8 to 3.6, everything is accepted. And that's one example. So that means it's a perfect drawing.
Yeah.
Right. So let's move on to the next spot. Okay, we did this. Okay, next question actually. Toughness of a sample of a material can be measured using an isotope impact test. Okay, this might be some test. What is meant by tough material? Well, tough material means it is capable of withstanding stress, or it has, we can say that it has very high ultimate tensile stress. So we just need to state it. So material that can withstand a lot of stress without breaking. Material that withstands a lot of stress without breaking. Or has high ultimate tensile stress. Because ultimate tensile stress, this is your keyword, so you just mention it as well. High ultimate tensile stress. This one, this option is the one which we wrote. Force, stress, same thing, okay? Impact, stress, force, same thing. We got the mark. Now, next part says the diagram shows an isotope impact tester. A sample of the material is placed in the tester as shown over here. A pivoted hammer of mass m is released from a height h and strikes the sample. The sample breaks. The height h to which the hammer rises after the impact is measured. Okay. So this height is what they are asking, that the height h to which the hammer rises after the impact, it is measured, this one. Name the point on the hammer to which the height h and h are measured. What point is this? Well, this point seems like the point of the weight or the center of gravity, but let's look at it. Yep, that's the answer, center of gravity. Center of gravity is the point from which the h and the capital and small h are measured. State an equation for the energy transferred to the sample. The energy which is transferred to this sample would be the kinetic energy, right? The kinetic energy of this block, but we don't have the velocity of the hammers given to us. So what we actually can do is we can convert the potential energy of the hammer. Initially it had this much potential energy, mg capital H, and now finally it has mg small h. So the difference is the energy transferred to the sample, correct? That's
Yeah.
actually the elastic potential energy that got converted. So the energy transferred is equal to mg capital H minus mg small h. This is your answer. Okay, same thing. They just took out the m common. Moving on. The impact test can be used to measure the toughness of steel at different temperatures. The toughness of a particular type of steel varies with temperature as shown in the graph over here. So as temperature rises, the toughness rises to a certain value and becomes constant over there. And as temperature falls, it decreases to a certain value and then becomes constant there. So the brittleness and the malleability of steel also varies with temperature. With reference to brittleness and malleability, explain how the toughness of this type of steel varies with temperature. Okay. So now we need to just describe and explain. I think that's explain. Okay, we need to explain with reference to brittleness and malleability. Explain how the toughness of this type of steel varies with temperature. Toughness means how much force it can withstand over impact. And in other words, according to the marking scheme as well, that how much energy it could absorb. And yeah, that's also true, because the greater the energy it could absorb, the greater would be the toughness, or the greater the force it could withstand, the greater would be the toughness. Okay, because force and energy, they are proportional to one another. If you look at this formula, F into S, they are proportional. But anyways, work is equals to force into displacement is what I mean. But regardless of this formula, look at the question. It says brittleness and malleability. Brittleness means how quickly it breaks. Malleability means it changes shape, meaning uh, the range of plastic deformation it can undergo before breaking. We did an MCQ on malleability as well, right? The malleable is the one which has a high range of plastic deformation, and it can undergo significant plastic deformation. Clear? So malleability means the ability to undergo plastic deformation. Brittleness means the ability to break. Now, it also varies with temperature. And now, This graph tells us about the toughness of the steel. That at higher temperature, its toughness is greater. Greater toughness actually means that lesser chances of breaking, right? Greater toughness means lesser chances of breaking. Just a second. Yeah, so greater toughness means lesser chances of breaking. And when are there lesser chances of breaking? When the object is malleable, or is it brittle?
Brittle.
Brittle means more easily breakable.
Lesser chances than the malleable.
Malleable, yes, correct. And over here, there are greater chances of breaking. Greater chances of breaking. So is it going to be more malleable, or will it be more brittle? Greater chances of breaking means
Brittle.
it's brittle. Okay. So think of it this way: the temperature, as it increases, the toughness increases, and at the same time the malleability increases. It becomes more malleable and it is less likely to break. But as temperature decreases, the ability to undergo plastic deformation or the malleability decreases, and the object becomes more brittle. As the temperature decreases, and the chances of breaking or the toughness also decreases, and therefore the chances of breaking increases as the temperature decreases. Now read the question again. It says, with reference to brittleness and malleability, explain how this toughness of the steel varies with temperature. So I'll write down the answer. At higher temperatures, the toughness increases. Okay, that's the first statement. Or I should say that as temperature rises, the toughness increases. Yeah, that's a better answer. The higher the temperature, the greater the toughness. At high temperatures or at higher temperatures, the malleability increases. So the extent to which it can undergo plastic deformation also increases. Therefore, toughness at higher temperature increases. Then at lower temperature, the steel becomes brittle, and hence easily breakable. So toughness decreases. That's the answer. But if you look at it carefully, it's just 3 points that I've written over here. I've said that as temperature rises, its toughness rises. At higher temperature, it's because the toughness is high because of the high malleability, and at lower temperature, the toughness is low because of greater brittlity or more brittle, or the object becomes more brittle. If you look at the answers, temperature increases, toughness increases. At lower temperature, it is brittle. At higher temperature, it is malleable. And that's all. That's all you need. Okay?
Okay.
So I hope you would have learned this answer now.
Yeah.
All right. Do not forget it. Okay, projectile. Okay, 15 says in a game of cricket, a player hits the ball which takes path B. Okay, this is your path B over here. Air resistance acted on the ball as it traveled through the air. If there was no air resistance, then it would have followed path Q. Draw a free body diagram, free body force diagram for the ball when it is at the position marked X on the path P. Okay, so when the ball is over here, what's happening? How many forces are acting on it? Okay, so basically you have your weight acting over here, and since air resistance is not negligible, air resistance would also be acting on the same ball. Air resistance, where does it act? It acts in the opposite direction to the velocity. So if this is your velocity acting in this direction, then the air resistance or the frictional forces acting must be acting in this direction with an angle theta in between them. So these are the two forces. These are the only two forces acting on this ball, so you just need to draw them out. This is your W, and this is your frictional force. Okay, some students, what they do is they make the frictional force like this, which is incorrect. Okay, the frictional force always opposes the direction of velocity. Clear?
Yeah.
Weight and drag, air resistance, frictional force, etc. So label it as well, it's better. Fr is your air resistance, and W is your weight. Now explain the differences between these two paths, P and Q. P is in the presence and Q is in the absence of air resistance. Okay, what happens to the horizontal distance as air resistance is considered? If air resistance is negligible, then what was the horizontal distance? What is the horizontal distance called? It is called the range of the projectile, right? And what is the vertical height called? It's the height of the projectile, the maximum height of the projectile. Now, both the heights and the ranges are changing as air resistance becomes significant, as it becomes appreciable. So now in path P, the range has decreased significantly due to frictional forces, and its height has also decreased significantly due to the same reason, frictional forces. Now, what really happens over here, we need to explain why the paths are different. So basically the air resistance, first of all, the horizontal component of velocity and the vertical component of velocity is due to the changes in these two components, right? The horizontal component of velocity, since air resistance is not negligible, therefore it keeps on decreasing. V cos of theta, it keeps on decreasing until it reaches a smaller value than it originally had. Whereas the vertical component, in addition to the weight acting against the vertical component of velocity, there's the frictional force as well acting against the vertical component of velocity that reduces the height of the ball. So just a second. Right, so that's the answer given to us. These are actually the 2 points explained over here. He told us the lesser the distance is traveled, meaning the range is less. Okay, 1 mark for that, for writing these points. This is 1 mark point. And then the horizontal component of velocity decreasing because of the frictional forces. A ball is slowing down horizontally, or ball has a horizontal deceleration, or ball is in the backward horizontal force, or ball is in air for a shorter time. Any of these are acceptable. I think this is the more suitable one. For path B, the maximum height reached is lower. The maximum height also has the mark. The height is called the path. Okay, the path is lower, but you don't need to go over there. That this is enough. And then the vertical deceleration has become greater. Why has it become greater? Because in addition to the weight, causing the deceleration, there is the frictional force as well. So the average vertical velocity is lower, or as the ball rises, there is a greater downward force. For horizontal component, allow v x direction, and for vertical, allow y direction. Allow the opposite comparisons for path Q. So these are literally the 4 points you need to write in your answer. but you need to write them in a paragraph form. Okay, so explain the differences in between these two. So for P, sorry, not R, for P, range is lesser due to decreasing or due to decelerating horizontal component of velocity. You can also mention that the deceleration is provided by the frictional force, deceleration due to friction. Whereas you can also mention that the height, the maximum height in Q is greater, or in P is lesser because greater decelerating vertical force is acting on it this time. Decelerating vertical force acts. Okay, decelerating vertical force acts. Okay, the weight plus the friction. Okay, both of them are acting on it in the vertical direction as well. And you might be thinking that how is friction acting in both vertical and horizontal directions? Well, the answer to that is because friction splits itself into the horizontal and vertical component. And then the horizontal component, it acts against the horizontal velocity. The vertical component acts against the vertical velocity. So due to this, so lesser maximum height in P. And that's literally everything you need for 4 marks. Part B says the ball was given an initial velocity of 35 meters per second at an angle of 25 to the horizontal. The horizontal distance from the player to the boundary is 85 meters. The player scores 6 runs if the ball lands beyond the boundary before it bounces. Determine whether 6 runs will be scored, ignoring the effect of air resistance. So we need to see that what's the horizontal distance that the ball will travel in order to allow the person to get 6 runs. Okay, if this distance turns out to be greater than 85, then yes, of course, he'll get 6. And if it is less than 85, then no, he won't get the 6 runs. Maybe he might get the 4 runs, or he might get out, or he might get cashed, etc. So let's see. So this is your, and we need to ignore the air resistance, so we can just do our simple calculation. This is your 35 meters per second given to you. Angle given to you is 25 degrees. Okay, now what's the horizontal component of this ball? So the VH, or the horizontal component, is going to be 35 times cos of theta. Theta is 25 degrees. So 35 cos of 25 is, can you give me the answer?
31.7.
30?
1.7.
1.7. Okay. Can you give me a number after this? Two decimal places?
Yeah, 31.72.
Okay, 31.72 meters per second. Now this is your horizontal velocity that you got. Now all you need is the time it took for the ball to cover this distance. How will you get the time? Well, for the time, by now you should have this thinking that you'll need to find out the vertical component of the velocity, which is going to be 35 times sine of 25 degrees. And that vertical component can be used to get the time. Why can it be used to get the time? Because remember, the vertical motion is similar to this ball which is thrown upwards to the maximum height, right? Throwing it upwards to the maximum height means its final velocity is 0. Its initial velocity is this much, 35 sine of 25 degrees. The maximum height is not given to you. So you need to use a formula that does not have height in it, but must have time and acceleration is the same 9.81. It cannot change. And in this case, it's going to be negative. Okay, so which formula has these values in it and does not have displacement in it? It's V is equal to U plus AT, right? We can use this formula. Now V is 0. Initial velocity, initial vertical velocity, or the vertical component of velocity is 35 sine of 25. Plus the acceleration is going to be negative of 9.81. Why negative? Because the ball is going up. Will its velocity increase or will it decrease? What's the answer? As the ball,
Decrease.
yes, it will decrease. Decrease means acceleration is negative. And if it is negative, then you could just solve this question. It's negative 9.81. So 9.81 time is equals to 35 times sine of 25. Get the value for the time, which is 35 sine of 25 divided by 9.81. And can you get me the answer to this?
Wait, 35 into sine 25.
Yes. And whatever you get, just divide it by 9.81.
One point five one.
Seconds. Okay, we have the time. Now the time it took the ball to reach its maximum height. This is the time it took the ball to reach its maximum height, right? Meaning this is just the time of one part of the journey. What's the total time? Is gonna be twice of this time or not? The total
Yeah.
time of the journey is gonna be twice of this time because range actually means the total horizontal distance. So the total time is gonna be twice of this. So calculate the total time, please. Total time. Now this is also a common error which the students do is they just use this time, which is wrong. This is just the time for half of the journey, not the whole journey. So it's gonna be somewhere around 3 point something. What's the answer? 1.5.
1.3.
Yeah, just multiply the answer by 2. It's 3 point something, right?
3.02.
All right, 3.02 seconds. Now once you have the total time and you have the horizontal component of velocity, now you can calculate the horizontal distance that the ball has traveled, which is the range of the ball. So S is equals to VT can be applied, right? S is equals to horizontal velocity multiplied by the time. Horizontal component of velocity is 31.72 multiplied by the time, which is 3.02. And the answer to this turns out to be how much?
95.79.
95.79 meters. So is this greater than the one which they have given us, or is it less than the one they have given us? They have given us 85 meters. The boundary is at 85 meters. Is this greater than 85?
Yeah.
So will he get a 6 or not?
Yeah. We will.
Yes, since range is greater than 85 meters, yes, batsman gets a 6. That's a third umpire's decision. Okay, let's check it out. 96, yep, that's the answer, correct. They also did the same thing. They also asked us to calculate the full flight time, which is a 3.02, and then use this formula and then this. Easy?
Yeah.
A student says Newton's first law of motion as if no external force is applied, there will be no motion. Criticize this statement. Oh no, that's not always the case. The Newton's first law says, by definition, that any body will continue to move in a straight line. Oh, okay, even before that. even before that, it says, Newton's first law says that any body will remain in the state of rest So basically, the Newton's first law of motion, it was Newton's first law of motion, which actually says that it will continue to move in a straight line or remain in a state of rest if there is no net force or no resultant force acting on the body. So external force is not always the case. Instead of external force, he should have used the term resultant force. You have to write it in an entire answer, okay? I'm just writing down the key points. Instead of the external force, he should have used the term resultant force. And instead of using the term no motion is not always the case. No motion is not always the case. The body can have uniform motion in straight line. Okay. Part B. The diagram shows a person pushing a trolley and pulling a trolley. This one is pushing and this one is pulling it. Now the angle theta between the arms of the person and the horizontal is the same for both of them, pushing and pulling. The corresponding diagram showing the forces on the trolley for pushing and pulling are shown. Now this is a person, he's pushing it, so it's acting in this direction. This person is pulling it, so it's acting in this direction. If you look at, okay. The diagrams show a person pushing a pulley, pushing a trolley and pulling a trolley. The angle theta between the arms of the person and the horizontal is the same for both pushing and pulling. Corresponding diagrams show the forces on the trolley pushing and pulling down are shown over here. Okay, this person is pushing it, this is a force which is applied. This person is pulling it, and this is a force which is applied over here. This is pushing, that's pulling. It can be assumed that the frictional force between the trolley and the ground is proportional to the normal contact force of the ground on the pulley. So basically this normal contact force that is acting, which it has to stay constant, but this normal contact force and the frictional force on the trolley are proportional to one another. Explain why pulling the trolley a certain distance requires the person to do lesser work than pushing the trolley the same distance. Now see, pulling, why will the pulling require lesser work? It would require lesser work if the frictional force that the trolley experiences is lesser than the frictional force in this case. That's the only case when it will require lesser work. So we need to develop an answer in such a way which results in the frictional force becoming lesser, and so hence lesser work done. Over here, this is the direction of the force which is applied by the person. This force can be divided into its components, meaning resolved into its components, the vertical and the horizontal component. The vertical component is in the direction of the normal contact force, and the horizontal component is in this direction, which is required to do the work. Okay, this is the force of the person on the trolley is Fm. Okay, this is the horizontal component Fm, and this is the normal contact force, and this force, the vertical component of this force applied by this person, this one, this is Fm, the horizontal component, if this angle is theta, so this is Fm cos of theta, and that's the Fm sine of theta. Now, if Fm sine of theta is acting in the same direction as the normal contact force, then what do you think? Will the normal contact, the total force, the total normal contact force in this case, will more of it be required to balance the weight, or will lesser quantity will be required to balance the weight? If the vertical component is acting in the direction of the normal contact force, what will happen to the net normal contact force in this case? I can say that the total will increase, but what happens to the value of the normal contact force? The normal contact force plus F sine of theta will balance out the weight in this case. If I were to make an equation for the for the normal contact force, it's going to be W minus F sine of theta. So in other words, I can say that this F sine of theta is actually balancing out the weight. right? With the normal contact force. This is the equation I get for the normal contact force in this case. Whereas for the left side, if you look at this force, this is the force applied by the person. Its vertical component is acting against the normal contact force, right? The vertical component is acting downwards. It's F times cos of theta is acting downwards, and then sorry, F sine of theta is acting downwards, and F cos of theta is acting to the right. Now, in this case, the normal contact force is the sum of the weight and the F sine of theta. So in both the cases, look at the equations of a normal contact force. In case of pushing, it's W plus F sine of theta. In case of pulling, it's W minus F sine of theta. So in both the cases, in these two diagrams, which one will have a greater normal contact force? The right one or the left one?
The left one.
The left one will have a greater contact force. And they told us in the question that this normal contact force and the frictional forces are proportional to one another. So can I say that the frictional force over here, due to the greater normal contact force, is also going to be greater?
Yeah.
And if this frictional force is greater, then that actually means more work will be needed in this case. More work needed. But on the right-hand side, lesser work would be needed because now the normal contact force has decreased. Normal contact force has decreased. So next time when you go to the airport to push your trolleys, try pulling it and not pushing it. And they'll think you are weirdo. Okay, so explain why pulling a trolley a certain distance. Okay, the same distance. Okay, so let's frame our answer. So first of all, the normal contact force, normal contact force in the diagram on the right, in the pulling case actually, in pulling the trolley,
Also, sir, how many minutes left till this class gets over?
we still have, so now normal contact force in pulling the trolley is lesser than that of pushing the trolley. Since vertical component of force applied is also in the direction of the normal contact force. In case of pulling. Since frictional force is proportional to normal contact force, so frictional force becomes lesser than the normal, becomes lesser in case of P than Q. And if the frictional force is lesser in case of P than Q, so lesser work needed in overcoming the friction. In case of P. The marking scheme. Pulling gives an upward force on the trolley. Okay, we did that. The upward component of force. Normal contact force is lesser, friction is less, so less force is required by the person due to friction. Meaning less work is done against friction. Friction is the horizontal, where F is the horizontal component, F is the friction. Well, we did combine these 2 points in our answer by saying that less work is done against friction, but it's better to go with the marking scheme by saying that less force is required to pull the object, or we could say that lesser horizontal component of force is needed, or lesser force is needed, but say if f prime, the f prime which they have given us, lesser that is needed. Lesser force is needed to pull it, and work done is equals to force multiplied by distance, where F is actually your frictional force, or the force which is required against which you are doing the work. Okay, so this completes the answer. A student determined the Young modulus of a material in the form of a wire using the equipment shown. The control wire with a constant load was used as a comparison for measuring the extension of a wire under test. So extension needs to be measured, and there is a constant load or constant force on that wire. This is the wire under test. This is the control wire. This is a spirit level for keeping it horizontal. This is the applied force, and this is a constant force. Every time a known weight was added to the applied load, the micrometer was adjusted until the spirit level was horizontal. The movement of the applied load was the same as the movement of the micrometer. So the greater the movement of the micrometer. List any additional measurements that you are required for a student to determine the value for the Young modulus of the material. Formula for Young modulus is FL over AE. So A is cross-sectional area, the micrometer will give you the cross-sectional area. L is the length, and for the length, they haven't given any instrument. So for that, we can use a meter rule. For extension, they told us that the micrometer movement is the same as that of the extension. Movement of the applied load was the same as the movement of the micrometer. So micrometer will actually give us extension, but for the area as well, you'll get that. But what about the force? For the force, meaning the load, you'll need a mass balance as well. Wait, they want us instruments? List any additional, okay, they want measurements, sorry. Not the instruments, the measurements. So yeah, the original length by the meter rule, and the diameter also not measured. Why not measured? Because the micrometer which is used over here, this one, this is not for measuring the diameter, but rather it's for measuring the extension. So that's why diameter is asked. Now it says the student plotted a graph for the applied load against extension of the wire. Sketch a graph that you would expect for the student to obtain. I mean, this is a force extension curve or a graph, force extension graph. So what do you think? It's going to be a straight line passing through the origin, and then it will start curving towards extension. But will it curve? This is a control wire and it is going down. Well, yeah, I think they should allow the curving. Okay, they didn't allow it. Just a straight line passing through the origin. So they've assumed that it's within the limit of proportionality. And it is for 1 mark, so yeah, a straight line passing through the origin should be sufficient. Sketch a graph that you would expect. Plotted a graph of load against extension. You have the control load and wire comparison, extension under test. And yeah, of course, that's also a reason, because if the person is applying a load, he will be applying a load within the limit of proportionality, not beyond that. Otherwise, it would disrupt the experiment for measuring the Young modulus. Okay. Now explain how the student can use the graph to determine the Young modulus. Okay, that's easy. What's Young modulus formula? It's FL over AE. In this graph, the F over E, where is this F over E in this graph? This is force, this is extension. F over E means the gradient of this graph, yeah, right? So multiply the length upon area by the gradient of the above graph. And for the area, you can use the formula pi d squared upon 4, because of course you need to mention this. Area cannot be measured. You get the area, you get the length, divide them and multiply it with the gradient, you'll get the Young modulus. And they've done that same thing. Oh, you have to use symbols must be defined. Okay, so you have to mention what these symbols actually mean. And remember this L, just writing length is not sufficient. You have to write the term original with it, because extension is also the length. And this is a simpler method. Remember, we did this one. A simpler method to determine the Young modulus of a material in the form of a wire is shown. The position of a marker along the meter rule is recorded each time the applied load is increased. So as this increases, the position of the marker is labeled, or it is observed and then seen how much it has extended. Explain two advantages of using the first method rather than the second method to determine the Young modulus. So we'll need to see what the two advantages are. Okay, let's look at the first method first. Okay, in this first method, we've got the spirit level, and then it's a quite a technical method and a more complex one. So of course, this accuracy of this method is going to be greater, but just writing accuracy won't be sufficient to get our mark. So in the second method, okay, first of all, in the second method, you have the meter rule for measuring the extension. If you look at it carefully, this is the meter rule that you are using for the extension in the second method. And in the first method, it's a micrometer that you are using for the extension. So which one is more precise? Which one has a higher precision or a better,
The right one.
the micrometer, right?
Yeah.
Yeah, so the two advantages are, first, micrometer is used, right? Micrometer is used in the first experiment. We need to explain them, okay? Used in first experiment. Which has a greater precision. Do you know what precision means? Precision means least count. It has a smaller least count. So it can measure even smaller changes than meter rule. Okay. It has a greater precision than the meter rule. Meaning greater, instead of writing greater, it's better to use better. Okay. It has a better precision, because greater precision actually means the smaller the value of precision. So that actually makes it a bit confusing. It's better to use the term better precision or resolution. Then, or if you remember the least count of micrometer, you could just mention that 0.001 millimeter as opposed to that of the meter rule, which is 1 millimeter. So this is smaller, right? The smaller the value, the better the precision. Then over here, this is the wire under test. This is the force which is applied over here. The force can be, this force will give you a measurement of the tension in this wire, basically the force applied on the wire. Whereas in the second experiment that we have over here, we've got the pulley over here. This pulley, if it is not frictionless, then that would actually mean not all of this applied load would be applied on the wire, right? So that's also a disadvantage of this method, that in the first method you could more accurately measure out the tension, whereas in the second method you have the pulley. So the pulley might not allow you to measure it accurately if it is not frictionless. So more accurate measurement. And I think that's enough because it's just for 4 marks. So 2 points identifying and explaining are enough. And is this clear? Any question?
Yeah.
Okay. 18. The flow of blood around the body is mostly laminar. Laminar, remember, uniform flow. Speed of the blood in the body is greatest on leaving the heart. That's because of the greatest pressure. And at this point, turbulent flow can occur. Why can turbulent flow occur? Well, the reason for that is because valves are there, and the valves, they can disrupt the flow of blood, but you don't need to know that in physics. Add to the diagrams to show laminar flow and turbulent flow. Well, this is easy. For laminar, just use a ruler and draw out a straight lines. They must be parallel to one another. Okay, make sure to use a ruler. I don't have it right now, but you have to use a ruler. And for turbulent flow, it has to come like this or like this, like a non-uniform flow. Could be going in any direction you want. Okay, well, it's usually going like this, coming like this, going forward and then returning back. And in heart, well, I did study this in my MBBS, that there are valves. The valves act as barriers in front of the blood. So the blood goes like this and come round the heart. But you don't need to know the valves and stuff. That's part of MBBS. So for this, you just need to know this. You just need to draw the diagram of turbulent flow. Then a student wishes to estimate the power output of the heart. He argues that the heart has to pump out blood at a speed v and raise it to a height h above the heart. He proposes the following equation, where q is the volume of the blood passing a point where per second, and rho is the density of the blood. Derive this equation for P using the principle of conservation of energy. Okay, Q is the volume of the blood passing a point per second. They gave us the volume per second, and rho is the density of the blood, and we need to derive this expression. And if the student can do it, we can definitely do it too. We need to find out the power output of the heart. Okay, and blood is being pumped at a speed v and raised to a height h. Raised to a height h actually means it's converted into gravitational potential energy. Speed v means it's converted into kinetic energy. So now, what's the total power? The formula for power is work done per unit time. Okay, now remember one thing. We don't have work done, we don't have the time. So first we need to find out. Yes?
Yep.
Okay, so now first we need to calculate the total work which is done by the heart. First of all, the heart is converting it into kinetic and potential energy. So it's going to be kinetic energy plus the total potential energy. Now the kinetic energy formula which we've been studying is half mv squared, and the potential energy is mgh. Now h is basically the height above the heart, so we have that. G is also known, but what is the m? M is the mass of the heart, and m over here is also the mass of the heart. So we need to get an expression for the mass of the heart, but we do know the density of the heart, right? Sorry, not the heart, the density of the blood that the heart is pumping. Density is mass divided by the volume. Volume, which is given to us, is Q. Q is the volume that is passing per second. So if Q is the total volume, the total mass that is passing through a point per second is going to be rho multiplied by Q, right? This is the total mass. Total, you have to write down this the meaning of them as well during derivation. Total mass of blood passing through a point per second. Passing per second. Okay, now once you have this mass of blood that is passing through a point per second, you can take it and plug it in here instead of the m. It's going to be half times rho times q v squared plus, again, instead of the m, you're going to write rho q m, sorry, not m, gh. Okay, now is it similar to the one which they have asked? It is actually the one which they have asked. This is the formula for pressure, sorry, for the power. Why is it also the formula for power? Because listen, they told us it is the volume of the blood passing per second. Per second. Per second means it's per second, means it is per unit time. Per unit time actually means this is actually the work done per unit time. So this is actually the power, expression for power. Understood? Is this understood? Hello?
Yeah.
Did you get it?
Yeah.
All right. Part 2 says calculate the power output of the heart when pumping the blood to a height of 0.4 meters above the heart. Assume that the speed of the blood has not changed since leaving the heart. Speed has not changed means the change in kinetic energy has become what? What has it become? Answer me. Has it become 0 or not? Yes, definitely I can say that. So this entire factor becomes 0 because there is no change in kinetic energy. So power is actually just equal to rho times Q times G times H. Now the rho is the density, which is 1100. The Q is 95 cm cube per second. Okay, cm cube per second. You need to convert the cm cube. What does centi means? Centi means 10 raised to the power of -2. But is this cube? Is this cube? If this is cube, then you have to cube this as well. Okay? That's how you convert the centimeter cube to meter cube. Just multiply by 10 raised to the power -2 cube.
How do you GH?
Sorry?
How do you get it?
But then that velocity will stay constant. So this means that the heart has actually converted some of its energy into the kinetic energy of the blood and then use some of it to raise it to height. So this means it has done some kinetic energy as well, meaning it has done some work in giving the blood some kinetic energy. So yeah, you have to add the kinetic energy as well. So it's going to be half times the rho of the blood, which is 1100 plus Q, which is again 95 raised to the power of, wait, it's, yeah, 95 raised to the power of -6 multiplied by 9.81 multiplied by, wait, not 9.81, multiplied by velocity squared. Velocity given to us is 0.45 squared. Can you add this factor as well in there to your answer and give me the final answer then? Half multiplied by 1100, okay, it's not plus, okay, half multiplied by 1100 multiplied by
I add up
95. Okay, let me write it again. It's 1100 times 95 times 10 raised to the power of -6 times 0.4. Then add it to half times 1100 times 95 raised to the power of -6 times 0.45 squared. Yes, now this thing. Give me the answer to this.
that's 0 point in brackets.
45 squared. Do not consider this part, okay? That's the final till here.
0.011.
I think you did multiply the last part as well.
No, I didn't.
Please just leave it till here.
I did that way.
Can you do it again, please? Times 0.4 plus half times 1100 times 95 times 10 raised to the power of -6 times 0.45 squared. 0.0148. That's still not the answer which they gave us. It's 0.42. Wait, there is just slide. Oh wait, there is miscalculation. I didn't put the 0 over here. We can use the same formula. So now over here, for the raw, we can use the density of the blood, which is 1100 kgs per meter cube. Then the Q is actually the volume. It's going to be 95. It's cm cube, so convert the cm cube to meter cube. So for centi means 10 raised to the power of -2, and you have to cube it as well because that's cube, and then multiplied by v squared. It's 0.45 squared. Then add it to rho QGH. Rho again is 1100, Q again is 95 raised to the power of -2 cube, and then GHG is 9.81, and H is the height given to is 0.4. And now get the final answer by just adding all of them up.
Calculator.
Yeah, please calculate it and tell me. I got this answer. And that's the answer. Okay, so it's basically work might be done against the frictional forces as well, or the blood might be facing some resistance of the blood vessel walls, correct? So which is actually the blood pressure. So it's not actually the blood moving up that height without any resistive forces. So that frictional forces were not counted. If you remember, the formula for power is going to be change in kinetic energy upon time plus change in potential energy upon time, and plus frictional forces, work done against frictional forces upon time. This is the third factor as well. We did this entire equation in our theory class, but this third factor has not been counted in the above calculation. So yeah, so work will be done against frictional forces or resistive forces against the walls, resistive forces work done against resistive forces. So P will have a greater value. All right. And I think this is the last question, but we can do that in tomorrow's class. We can end the class here.
Next class can we do unit 3.